Hi, today's video is about garbage collection in Java. But I should warn you, this is more like a theoretical video than anything practical, as I would have liked to show you using from some programming examples or something like that. But this is going to be a theoretical overview of how garbage collection works in Java and what are the garbage collectors out there and what are the purpose of those and how to use them. So I'll try to keep this as short as possible so that the topic is not boring, but let me know your feedback once you go through this. So let's start. So before we start, we should know why there are garbage collectors in languages like Java. So before Java, the most popular programming language was either C or C++. So if you have a history of programming in those languages, you would know that you are supposed to manage your own memory in those languages. So for example, in C you have the method calls like realloc, malloc or calloc that would allot buffer memories for you. You have to specify how much memory you need for your program and say that in those API calls, and that will get you a buffer of memory for doing something like creating a linked list node or something like that. But at the same time, at the end of your program, at some logical point, you are responsible for freeing that memory as well. So let's imagine like a big batch processing application written in C language that keeps on allocating buffer memories, and sometimes it forgets to free the memory and eventually that will cause memory leaks and a lot of issues in the application. So also in C++ you would use constructors new and destructors to release your resources. So those are some things that the programmers had to take care or worry about whenever they were implementing things in languages like C and C++. But Java came with automatic memory management through a thread called garbage collector, and most of the modern languages have it, which in background runs and watches your memory for you, sort of watches you back and removes what can be removed. So it basically works on a couple of hypotheses, which is that most objects soon become unreachable. That means the objects are generally created in context of something like a small if block or something like within the context of a method. So most of the objects are created like that whenever you write your code. And so those objects are out of scope as soon as the method execution is complete or the if block is over. So those can be garbage collected. And next is references from old objects to new objects only exist in small numbers. So that means the objects that live forever or live for a long time in your application doesn't generally refer to freshly created objects. For example, let's take an object that would survive for a long time in your application, which is probably a cache. And generally in a cache you would store things. Whenever the cache was created, you would have already populated things you wanted to cache, and you will just carry on. You probably won't put anything new in the cache in later period of the application. That's just an example. So those are the two hypotheses that drives the whole garbage collection implementation. So there are a couple of terms that we should be familiar with. One is live object. So live object is an object in your application that can be referred by another object in your application. So that means, suppose we have a live object here that will be referred by another object here, and then that object will be referred by something else. And if you keep on traversing like that, you will reach to the root node of your application, which can be the main thread, which actually creates the whole object graph of your application. And dead object is unreachable object, which is kind of was created during a method call, and as soon as the method call was over, the object became out of context and it's just lying there in the heap as an object. So those are the unreachable objects. So going forward, we should know that there are some basics that we should know before we start to go to details about garbage collection. So objects are allocated in the heap of Java memory. So there is a heap memory in Java where whenever you call a new and allocate object, that is allocated in the heap. Also arrays are object in Java, so they are also allocated there. So things like static members, class definitions, class metadata, etc. are stored in method area of the JVM, which is basically the permgen or the metaspace in modern Java versions like Java 8. Garbage collection is carried out by a daemon thread called garbage collector. That's simple. And there is a API available in Java called system.gc, a static method call on the system class. So a lot of people think that just calling that would trigger a GC, which sometimes is the case, but there is no guarantee that that would happen. So that is, you cannot really force, in theory, you cannot really force Java to do the garbage collection by calling system.gc, or I think also runtime also has a static method like that for performing garbage collection. So moving on to the next point, which is about java.lang.out-of-memory error. So this is a runtime error that you would get if JVM is no longer able to allocate new object in the heap. So you will get an error which clearly tells what happened. Basically it says java.lang.out-of-memory error, heap space will be written after that. So indicating you are no longer able to use heap anymore because it's full. And that is a time when you will probably start looking for object leaks or memory leaks in your program. So that means even when you have garbage collector running in the background and doing this scavenging job for you, you can still have memory leaks in Java. So that's interesting. And so you should be aware of how garbage collection works to a certain extent, and what are the things you should do to avoid memory leaks in Java. So going forward, let's see what are the steps in garbage collection. So garbage collection basically involves 3 steps, which is mark and sweep and compacting. So mark is basically a step where the garbage collector walks through the object graph, which I talked about, which is basically will have a root node of your application. Suppose you have a class called application which got invoked at the beginning, and everything gets created from there. So that is the root node. And from that root node you have references to some other objects, and all of them refers to something else. So it's like a big graph in memory. So the garbage collector walks that graph and visits each node and marks whichever object is reachable as reachable, and whichever object is not reachable, it just leaves alone and moves forward. So next step is deleting or sweeping. So as the name indicates, is the step where things are cleared off. So whichever is marked as reachable is not touched, and whichever is not reachable, the garbage collector thread would just clean them off from the sweep them off from the heap, and thus reclaims the memory. But then comes the step of compacting. So compacting is the process where you try to arrange everything in order. So suppose we have a heap here. So let's assume heap like a big grid of something, and from in the grid you have you have unreachable object here, unreachable object here, unreachable object here. So you keep on cleaning them off. Then there are holes in the whole heap, right? So there are so suppose you don't have contiguous allocation. Suppose here allocation has happened, here you have removed something which is unreachable, then again some reachable objects. So to avoid this fragmentation, the compaction is done. So all the objects are arranged in order so that the free memory is at the end of the heap. So that is basically compaction. And if you have used the disk defragment tool that comes with Windows, you would have seen a graphic representation of how the disk files and the disk blocks which are non-contiguous, how it makes contiguous. So you would have seen that. So it's similar to that, the compacting step. And as you can imagine, that's a time-taking step because it has to go through the entire heap and then arrange the allocated space accordingly. So we'll come to that details very shortly. So let's proceed and see what are the generations in Java heap. So basically Java garbage collectors are called generational collectors. It's because it depends on the generation of your objects, meaning if the object is young or if the object is old, or did the object survive, how many cycles of garbage collection and things like that. So as you can see in this diagram, the heap is divided into two spaces. One is young generation space and the other one is old or tenured generation space. So the young generation, as you can see, is the place where objects are created initially. So young generation, as the name indicates, is for young objects, where the new objects are created. And young generation is further divided into Eden space. Eden is a place where new things are created. Actually, whenever you call something like new, say hash map, for example, that hash map objects is created in the Eden space, and it's called Eden because it's a reference to the theory of Genesis in Bible, where according to the books, the life was first created in Garden of Eden. So they just used that name. So it's called Eden space, where new objects are created. So there are then survivor space. That means suppose objects are allocated in the Eden space and the Eden space becomes full. That means whenever you call something like new hash map next time, you don't have any more Eden space to create that hash map. So that is the time small garbage collection kicks in and cleans up the Eden space of all unreachable objects. And all reachable object, it moves on to the survivor space, indicating it survived a garbage collection. So then Eden becomes free, and again you can happily allocate new objects there. So there are other purposes of why there are two survivor spaces. We will soon see that. So that is the division of young generation into three spaces. And then you have old generation, which actually holds objects that survives for a long time, are promoted into old generation. Suppose you created a cache in your application, which is supposed to stay there for the entire application's life. So suppose initially when you created your cache, it's created in the Eden space, and then it's moved to survivor space, and after a few generations of garbage collection, suppose it survives a lot of cycles of garbage collection, that cache object will be moved to old generation, where it stays, and if it is never unreachable, it just stays forever. And if it ever becomes unreachable, it gets collected by a major garbage collection, which actually runs garbage collection steps all throughout the heap. So in this slide, we saw a couple of very important points. One is the division of heap into young and old generation, and another one is minor garbage collections that runs in the young generation, and major garbage collection that runs across the heap. And at the same time, you should be aware that any steps of garbage collection, minor or major, they are called stop the world garbage collection. So both are stop the world. Only thing is that minor is running on a very small, a short amount of memory, and so it's not that intrusive. You won't feel that the application is stopping or something. But when the major garbage collection kicks in, it has to run from the entire heap from one end to the other and do the mark, sweep and compacting of the whole objects. So that would really cause a pause in your application for about seconds, which will be really undesirable. So those are some points that we should keep in our mind from this slide. So let's move on and see a little animation regarding garbage collection. So in this animation, what I'm going to show is how the Eden space minor garbage collections happen. And also you should be aware that this slide is only showing the young generation. It's not showing the old generation. Okay. So here I have the Eden space where objects get created. And here I have the survivor from space and survivor to space. So as your application runs, new objects get allocated in the Eden space. And when as the application runs, there are objects that become unreachable. I'm marking them as gray here. And then now the Eden space is kind of full. So at this point, when your application tries to create another objects and JVM tries to allocate something on the Eden, the allocation fails. And that actually causes one minor GC to run. And when minor GC runs, at the end of it has marked all the live objects as reachable, and those are moved into the survivor space. So when they are moved into survivor space, the unreachable objects are swept and cleaned up, and we are good. So this slide indicates after first cycle of garbage collection, what just happened. You have all the objects that survived one cycle of garbage collection, in the survivor space, and they all have a counter which says, okay, it survived one cycle of garbage collection. Now again the application goes and allocates objects in the heap, and along the way some things in the survivor space becomes unreachable, and more objects are allocated. Some objects are again becoming unreachable and stuff like that. And at this point the heap is the Eden of the heap is full, and there are some unreachable objects here, and there are new objects, reachable objects here, reachable old objects are still here. So at this point JVM tries to allocate yet another object, and it fails, and when the allocation fails it triggers yet another minor GC, and at the end of that minor GC all the reachable objects are marked as still as reachable across the Eden and survivor, and then they are all moved to the survivor 2. As you can see they are moved to the survivor space 2, and objects from survivor 1 is also moved into survivor 2. Okay, so this is how that movement happens, and now cleanup of these unreachable objects are done, and all the reachable objects are now in survivor 2 like this. So this indicates, okay, there are these objects that survived 2 cycles of garbage collection, and there are these objects that survived 1 cycle of garbage collection. So you might wonder why there is this multiple survivor space in heap. So the reason why that is there is because to avoid another run of compacting step. So as you can see, as and when the movement happens, they are arranged in sequential order, like or contiguous order, so to speak. So this actually avoids the need to run another compacting step that will be expensive. But instead, since you have to anyway move around the objects, you are just moving it away and ordering it one after other and avoiding the compacting step. So that is the purpose of the survivor spaces. And now let's see what happens in the heap. Again, new objects are created in the heap. Some things are becoming unreachable. These are again here. These are becoming unreachable, and then JVM keeps on allocating your objects whenever needed. And there are a lot of unreachable objects now in Eden as well as the survivor, and the Eden is sort of full now. And now you try to allocate one more objects, and that allocation fails. And at this point, one more minor GC gets triggered, and as a result, all the reachable objects are moved to survivor 1. So things are now moving back to survivor 1 from survivor 2, as you can see. So at the end of this, all the unreachable objects are cleaned up. So there are some things that you should be aware of. That the minor GC is very short because it's running quickly over the Eden space and the survivor space. And at the end of that cycle, objects are moved into the survivor space from one survivor to another, and then from there back to the previous survivor. And this reordering continues until a threshold number, say 16. Let's take 16 as the example. And at the end of that threshold, what will happen is whatever is survived, for example, see here the counter has incremented, indicating these objects survived 1 cycle of garbage collection, this survived 2 cycles of garbage collection, and this survived 3 cycles of garbage collection. So when the threshold is hit, saying, okay, if any object has survived say 16 cycles of garbage collections, they are promoted to the next generation, which is old generation, indicating, okay, these are objects that are really not going away, they are going to stay here for a while. So they are moved to old generation, as you can see in this diagram. So that is based on a max tenuring threshold, and all the objects that are living long in survivor or Eden, they are moved out into old generation, and there is some breathing space again back in the young generation. So those are the basic functionality of garbage collector and how it is implemented. So what happens when old generation gets full? So in very broad terms, when old generation becomes full, and suppose a certain person is near full, okay, so there is this garbage collector thread that keeps on watching old generation, sees, oh my god, my old generation is almost full, now I'm soon going to be in trouble. So at that point of time, the major garbage collection kicks in, which goes over all the generations and performs mark, sweep, and compacting, which is three of these steps it has to perform, and it has to perform across the heap. Suppose your heap size is say 8 GB or 16 GB, it has to run across the whole 8 GB allocated for JVM, and hence it can be a very time consuming operation, causing your application to halt literally. Okay, so as you can see, a lot of minor garbage collections runs in the background on the young generation, which are quick, so it doesn't appear to be really pausing your application. But the major generation, which is going to run through the entire heap, would cause your application to pause. So that's when we talk about performance with relation to garbage collection. So in performance, we have to be aware of two terms. Okay, so one is responsiveness or latency, and the second one is throughput. So responsiveness or latency is basically how quickly an application responds with a requested piece of information. For example, a website, you request something from the site and you get back the result page. So that request response cycle is basically the responsiveness. How much time does it take? Or that is also known as the latency. So applications that needs high responsiveness, like a UI application, it's not desirable to have long pauses for garbage collection. That will be a very bad user experience. So given that, we should approach the garbage collection with that in mind. And coming to throughput, so throughput focuses on maximizing the amount of work done by an application over a period of time. So it's not really one single request and response, but rather it's like things that an application does over a period of time, like a batch processing of say 10 million records of data, right? So that happens over a period of time, and you kind of take an average and see how much throughput you get. So in that kind of an application, some amounts of pause where the application is not responding, but after that it really quickly processes all the records that comes in, is okay. It's okay to have such a pause and achieve the throughput you want to have. So that is the difference between responsiveness and throughput. So with that in mind, let's go and take a look at the garbage collectors, the different kinds of garbage collectors that are out there in Java. So first is serial garbage collector. So serial garbage collector is generally a very basic garbage collector that comes with Java since right from its implementation, and it's used for a small amount of heap generally. And this garbage collector runs in a single thread, and that means your application will be running, suddenly it's paused, and a single thread of garbage collection of mark, sweep, and compacting runs. Again, your application runs, again paused, and a single thread of your mark, sweep, and compacting is done. So that is a serial collector. Now going to concurrent collector. Okay, concurrent collector is a thread that performs garbage collection along with the application. So that means as the application runs, this concurrent thread of garbage collection also runs, and it does not wait for the old generation to be full. So it keeps on running, and whenever it can do certain garbage collection step, it does. So it keeps on running with the application. It doesn't look for the percent of old generation that is used to kick in a major generation. So that means it is highly concurrent basically, and it does not really pause the running application for a lot of garbage collection step. It only pauses the application during mark and remark step. All the other things like sweeping, compacting happens in parallel with the application. So that is why it is called the concurrent collector. And next is a parallel garbage collector, which uses multiple CPU for the multiple cores of your CPU for performing garbage collection. That means the garbage collection itself is going to be fast because it's using multiple CPUs of your computer. So that means multiple threads are there that does the mark and sweep, but it does not run in concurrent with your application. It just sits there, and whenever there is a need of garbage collection, like the old generation is say 90% full, for example, this parallel garbage collector kicks in and runs parallelly and quickly does the garbage collection steps and lets the application continue. That is the difference between concurrent collector and a parallel collector. So basically, concurrent collector runs with your application and pauses only for mark and remark, but everything else happens in concurrent with your application and does not wait for the heap to be full to a certain extent. It just keeps on running in concurrent. At the same time, parallel uses parallel cores of your CPU and waits until the heap gets to say 90% full or whatever, and then kicks in, quickly does the garbage collection steps in parallel and be done with it. So that is the parallel collector. So when to use concurrent versus parallel? So concurrent garbage collector has to be used when there is more memory and then there is high number of CPUs, because it's a concurrent process that keeps on running with your application. So you should have a lot of CPU to spare, because apart from your application, you are letting the concurrent thread also to run. And when there is very short pauses of garbage collections are desired, that means if your application has to be responsive or if it should have less amount of latency, you should use concurrent garbage collector. And when do you use parallel garbage collector? If there is lesser amount of memory and the number of CPUs are less and application demands high throughput, then you would go for parallel garbage collection. So concurrent collector or concurrent mark sweep, CMS, in Java is known as low latency collector, which is one of the most favored garbage collector for most of the applications, most of the web applications, most of the financial applications. They use the concurrent mark sweep garbage collector. So as of modern Java implementations 7 onwards, 1.7 update 4, G1 garbage collector was implemented. So G1 means garbage first. So which is basically what was the need for implementing G1 garbage collector is basically to make it more predictable in terms of the GC process. You could mention in the command line how much time you would like the GC to pause your VM, and low amount of fragmentation or pauses, and it mixes the both parallelism, the goodness of parallelism, as well as the concurrent collection, and it results in better heap utilization. So what it does is basically the G1 garbage collection mechanism basically divides your heap into small regions of memory, and each of these region can be it can be a hidden space, it can be a survivor space, it can be a tenured space. And whichever region has a lot of unreachable objects, more garbage, wherever there is more garbage, that area quickly gets collected by the thread, and so that's why it's called garbage first collector. So it's kind of concurrent as well as parallel at the same time, and it's working on short pieces of memory regions, so it's going to be faster, and that way it can kind of take care of having minimal amount of pauses or stick to what you want to be the pause to be. So that is the G1 or garbage first garbage collector in Java 7 and 8. So here's a quick recap of what are those garbage collectors we talked about, which are out there in Java. So first one is serial collector. As we said, in this picture you can see the blue arrows are the application thread, and the application is running, and suddenly for GC there is a pause, and the single threaded garbage collection is done in mark sweep and compacting, and then the application is continuing to run, and then again the garbage collection kicks in, but there is a pause, and single thread of mark sweep and compacting happens, and the application runs. And talking about concurrent mark sweep, concurrent garbage collector, where your application is running and there is a short pause for marking phase, and other stuff like concurrent sweep, etc., happens parallel to your application. Compacting, everything happens in parallel to your application. Then when remark happens, there is again a short gap, short pause to your application, but the remark again runs in parallel, as you can see. So it should be a really shorter gap, and then the application also continues run, and the garbage collector thread is running in parallel with your application thread. And finally, the parallel collector does this. It almost looks like the serial collector where your application is paused, but garbage collection runs in multiple threads, in multiple cores of your CPU, and that's going to be faster than the serial collecting over here. And so the GC processes are to be shorter, and then the application continues to run. So you can really see the contrast between the parallel and concurrent collectors here. And G1, as I said, the the heap is divided into regions, and they are garbage collected in parallel fashion, depending on whoever has more amount of garbage. And again, the whole concept of young and old or survivor, hidden, all these things are out there in G1. Only thing is that they are all divided into small regions and are all managed externally, like a set of old generation or young generation hidden space, survivor spaces. So that is the 4 different kinds of garbage collectors available in Java. Now, given that, how do you really use these garbage collectors? So this slide, I'm just showing how you would use a given garbage collector in your application. Suppose you want to use the single-threaded serial garbage collection. You would use this option, -XX:+ use serial GC. So if you put that in your command line of your application, you are telling JVM to use single-threaded garbage collection on young and old generation. So it should be on a very small heap because it's single-threaded. So your application is running on a small heap. It's okay to use serial GC. Generally, nobody uses it. Now coming to parallel GC. Suppose you want to use parallel GC. You would use -XX:+ use parallel GC. So this means the young generation uses parallel GC. At the same time, note, the old generation continues to use single-threaded GC. So if you use this flag, the young generation is garbage collected in parallel fashion, but the old generation at the same time is garbage collected using single-threaded garbage collection. So coming to another flag called use parallel old GC. So use parallel old GC, if you put this flag to your application in the command line, this means both the young and old generations have multi-threaded garbage collection. That means suppose you are building a batch application where throughput is the most important thing, and you can kind of tolerate certain amount of passes for garbage collector. You can use parallel old GC, which will use parallel GC in the young generation as well as the old generation. Now use par new GC is the another flag which tells to use this will be used only on the young generation, as your name new GC. The new means young generation. So if you want to use the multi-threaded GC only in the young, you would use par new GC, and then use concurrent mark sweep GC. This is the concurrent garbage collector, as I said, which is the low latency garbage collector. And as you can notice, this happens only in the old generation. So concurrent mark sweep GC is only for old generation, and that's why you have a combination of use par new GC and use concurrent mark sweep GC can be used if you want to have parallel GC running in the young generation and concurrent mark sweep running on your old generation. So finally, there is use G1 GC, which uses the G1 garbage first garbage collector. So in Java 1.6 it's parallel by default, and since Java 1.7 it's G1 garbage collector. So let's step back here and talk about some things that the JVM provides. So in the Java language specification, there is something called Finalizer. So Finalizer is basically a method that is guaranteed to be called when the object gets garbage collected. So there is this method called protected void finalize method that can throw an exception. That method is guaranteed to be called when the garbage collection happens on your object. So this is kind of misleading because previously, like in the olden days, people used to put statements like database connection.close or iostreams.close, all this kind of expensive resource they used to close in the finalize method, assuming that will be anyway called at the end of execution, and it will be all these resources will be freed at that point. But see, the problem with using finalizer is that there is no guarantee when this will be called. See, though it will be called when the object is getting garbage collected, there is no guarantee of when the object will get garbage collected, right? So there is no real knowledge of when your resources will be freed and things like that. Suppose due to whatever reasons this object is in memory for a long time and it goes into old generation, it will never be garbage collected until it becomes unreachable, or it becomes there is a need to have a full GC run on, or major GC run on your application. So that means the resources that the object is holding unnecessarily will be held and will cause more pressure on the memory. So the basic advice is not to use finalize method for anything important. You can just put a log or something in that if you want to, but do not use it otherwise. And also there is a very interesting aspect of finalize method. What if you put something like this equal to new of your class name, right? Suppose you recreate the object in finalize, what will happen during garbage collection? This is a very interesting question. So whenever you try to resurrect the object by putting like this equal to new of some instance, what will happen is that the object is recreated in the memory. Okay, so at the end of garbage collection, your object is recreated and it's not garbage collected. But also you should be aware of one very important contract, which says finalize method is only called once for an object. So that means next time when this object is ready for garbage collection, and if it is garbage collected, the finalize method is not called at all. So that object is gone now. So that is something that that tricky scenario you should be aware of. But do not try this at home, as they say. Okay, there is no need to put anything that creates the object back in the finalize method. So given that, let's go ahead and see some flags that are out there to tune the garbage collection parameters in Java. So this is to tune the heap basically, where you would say XMS value. XMS is to set the minimum amount of heap that needs to be allocated to your program, and XMX is the max amount of heap that is allocated to your program, default to 256 MB. And next is XX new ratio equal to some value. So that means how you want to divide your young and old generation. Okay, so in new ratio, suppose you say 2 means 2 by third will be used by tenured generation or old generation, and 1 by third will be used for young generation of your whole heap. XX new size equal to size means how much amount of size or memory you want to set aside for the hidden space, and max new size, how much amount of memory you want to set aside for hidden space. XX perm size is the perm gen size you want to define, how much amount of memory of the heap you want to give for things like metadata and static objects and things like that. And next is max perm size, how much maximum you want to give for perm gen. That is default 64 MB. So these are the parameters you would use to tune your heap, which indirectly would cause impact on the way garbage collectors are running, right? Suppose your old generation is very small, there will be a lot of minor GC collections, but it's okay if your application is not holding on to a lot of objects. If objects are created and kind of discarded, it's okay to have a very small hidden space. But if your application is going to keep objects for a relatively longer time, you should keep the hidden space bigger or the young generation bigger, so that the GC kicks in only after some time. By that time, maybe your object that has to stay alive for a long time would have become unreachable and might be subject to collection. So there are things like that you have to think about when you tune these parameters for in terms of performance. So going ahead to how do you print details of GC in your application? So there are certain switches that you can turn on by putting minus verbose gc, xx print gc details, and xlog gc, and a file name. So this is gc.log is a file name where a file will be created in your working folder of your JVM, and the details of gc is printed into that. Very verbose it is. Okay, but see, it does not have much of an overhead. But whenever you are looking at GC as a suspect of performance issues, you should use this. This is the only best way to look at GC and analyze it. So you can taste the GC log that this produces, and there are applications like the garbage collection log analyzer from IBM, and you can open it there in that application, which comes as an Eclipse plugin nowadays. You can open it that in that tool, and it will beautifully tell you with graphs and everything what is going on with your GC, and what are the things you might have to do, and some warnings if there are any, and some tuning suggestions it will give you. So also one more method to look at the GC details is using Visual VM. I hope you might have used Visual VM. Visual VM is a free tool that comes with your JDK installation, and it's in the, you can run it by running the command called jvisualvm on your command line if that is there in your path. So if you run that, it opens a graphical user interface where you can connect that Visual VM to one of the running Java applications. And then there comes a plugin called Visual GC that you can download and install on this, and it gives you a nice graph like this shown here, where it shows how your perm.gen looks like, how much it is full, what is the size of old generation, how much it is full, the Eden space and survivor spaces, and a live graph of what is going on your Eden, and how many allocation failure has happened, and how many times the object have moved around from survivor to survivor and moved to old generation. All these details you can see here, and it is very, very useful that way. And and finally, through Visual VM, you can kind of cause garbage collection by clicking certain buttons. It provides certain button here and there where you can click and cause garbage collection to happen externally, and that is something undesirable. But I know certain places where people, when they notice that their applications are running into memory issues, they would manually click this button and cause a garbage collection and kind of save that application for some more time. But at the same time, if you suspect a memory leak, you should better have the GC log. You should get the heap dump, and run a tool called JHAT, Java Heap Analyzer tool, and take a look at what is going on and try to understand what is there in your heap. So that is actually another topic for performance, which I'm planning to create with some practical examples. How will you look at performance, and how will you tune the performance using certain tools? That will be a longer topic, so I'm not going into details here of that. But there are tools like Java Heap Analyzer tool, JHAT, that lets you look at the heap and decide what to do. So coming back to garbage collection, so these are some nice tools that you can have, like Visual VM and GC logging, to exactly see what is going on with garbage collection. And also there are other tools available in the market, like Terracotta Big Memory. That's a software that you can install, and which will manage your objects outside the realm of garbage collection. So that means you can kind of move your objects outside the heap. Your objects will be moved outside the heap, and so that the garbage collector does not take much time at the same time and cause it saves you garbage collection process and things like that. So there are certain tools in the market out there which are all commercial. There are no free tools as far as I know, which lets you use direct buffer memory outside the heap to manage your Java runtime memory. So that kind of concludes garbage collection theory. I did not have any practical examples that I wish to show. So if you have any questions, please feel to leave me a comment. I'll try to answer. Thank you.